Okay, so in the previous video, we talked about protein folding in a polar environment. And we said that in a polar environment, the thing that's driving protein folding is the hydrophobic effect or the entropy. So now what we're going to do is we're going to look at protein folding in a nonpolar solvent, okay? And to orient you guys a little bit better, in a nonpolar solvent, what's going to happen when our protein ends up folding, so whenever we go from this unfolded state and go to this folded state, we're going to have the, remember how for the polar solvent we had a hydrophobic core and a hydrophilic exterior? In this case, it's actually going to be the opposite way. We're going to have a hydrophilic interior and a hydrophobic exterior, okay? So the hydrophobic region is going to be on the outside in a nonpolar solvent, okay? So keep that in mind when we're going through the problem. And again, what we're going to do is we're going to break it down like so, okay? And to orient you guys again, we're going to say that this is the backbone, okay? We're going to say that, again, our protein is going to have hydrophobic regions, which I drew in red, and then also hydrophilic regions, okay? So, of course, again, this protein is going to be much longer in reality, but just to prove this example, because we're going to cover all parts of the protein, I only drew one amino acid that's nonpolar and one amino acid that's polar. But we're, again, in a real protein, you're going to have way, way more amino acids than this. Okay, so let's get into it. So now what we're going to do is we're going to talk about the different bonds we're going to see in the folded versus unfolded state to, again, calculate the delta H. So looking at the backbone and trying to see what type of interactions it's making, I drew a bunch of benzene molecules. So the benzene molecules themselves are non-polar. You could have instead used hexane or whatever, anything that's non-polar, but I just used benzene. And we're going to see what type of interaction it's making with each part of the protein. So in this case, with the backbone, notice how the backbone, we said that the backbone is polar. So polar regions can make dipoles. And then whenever something is nonpolar, the only thing it can make is an induced dipole. So the interaction that's being made between the benzene ring and the backbone is dipole-induced dipole interactions. So we're going to say this is dipole-induced dipole interactions with solvents. Okay. Now let's look at the hydrophilic R groups. Well, again, we're going to have the hydrophilic R groups being polar, so they can form dipoles. And then benzene itself is nonpolar, so it can only form an induced dipole. So it's a dipole-induced dipole with the solvent. And then if we look at the hydrophobic R groups, now the hydrophobic R group is nonpolar, so it can itself form an induced dipole. And then the benzene ring is also nonpolar, so it's an induced dipole. So together, it's an induced dipole, induced dipole. And now again, we're going to magically close our eyes, and our protein is going to form its secondary structures, okay, which is like the alpha helix and beta sheets. It's going to form its tertiary structure, and we're going to get to our final native conformation of the protein, okay? So for the backbone, whenever it's forming the secondary structure, what type of bonds hold together the backbone atoms? Like we talked about in the last video, same thing applies. So hydrogen bonds are the things that are holding together a backbone, okay? So we're going to say that's H bonds. And now in this case, it's going to be with itself, okay? And again, well, we'll get to it. So it's going to make H bonds with itself. Now the hydrophilic R groups, remember, the hydrophilic region is now going to be in the core of our protein. It's going to be buried away from the nonpolar solvent. So in this case, hydrophilic R groups are going to interact with other hydrophilic R groups. So instead of interacting with the solvent, we're going to just put another hydrophilic R group. Okay, we're going to go like this, and I'm just going to put another serine. And notice how in this case, it's making a hydrogen bond, right? This is another H bond. So the hydrophilic R groups are going to be making H bonds with itself whenever the protein folds, okay? And then what we are going to now consider is the hydrophobic R groups. Well, the hydrophobic R groups, the protein's going to fold, and we're going to have the hydrophobic exterior in a nonpolar solvent, right? So because the outside of our protein is going to be hydrophobic, the R groups are going to interact with other hydrophobic R groups. So I'm going to draw that out like this. Oops. So we're going to put, instead of the solvent, we're going to just put other hydrophobic R groups. So I can put something like this. And again, because they're both nonpolar, they can form induced dipole interactions. Okay, so the nonpolar regions or the hydrophobic R groups are going to interact with itself. But remember, some of the hydrophobic, because our hydrophobic R groups are on the outside of our protein, some of them are going to also interact with the solvent or the surrounding solvent. So if I drew in the solvents here, we can have some of them interact with the solvents as well. So it could be with itself, okay, with other R groups, or it could be with the solvents as well, okay? So now we talked about the bonds in the unfolded versus folded state, and we're going to be breaking bonds in the unfolded state and forming the bonds in the folded state. So now let's calculate the delta H, which is H bonds broken minus H bonds formed. So, okay, now we're going from dipole-induced dipole bonds to H bonds, okay? Because we're going from dipole-induced dipole to H bonds, we're forming stronger bonds, and whenever we form, the stronger the bonds that we form, our delta H is going to be more negative. Remember, goal is to form stronger bonds and products, so that's a negative delta H. So over here, I'm going to just put a negative delta H because we formed, I don't know why I did it like that. Here we go. We're just going to go negative delta H. Okay. Now for hydrophilic R groups, we're going to again go from dipole-induced dipole to H bond. So we're going to also get a negative delta H. And then for the hydrophobic R groups, we're going to go from IDID to IDID. So the delta H in this region is going to be roughly 0. But overall, notice that the delta H for the overall protein itself is going to be negative, okay? Now if we're looking at the solvent, okay, the type of bonds that the solvent's making, if we're looking and just simplifying things, what's happening is that when it's interacting with the solvent, what's going on is that it's making dipole-induced dipole interactions, and then whenever it's in the folded state, it's making mostly induced dipole interactions. We're going to simplify that and say because these don't play a significant role to your delta H, we're going to say that it's roughly around 0, okay? But technically, it's a little bit more complicated than that because we're also making better bonds in the polar regions. So overall, we're going to say that the delta H of the system, because of this, is going to be negative, okay? So if we're going to tally our delta G equals delta H minus T delta S, remember, our goal is to have a negative delta G. In this case, our delta H is going to be negative, which is very good because, again, we want the overall equation to end up being negative. So we're in a great place now. And if you remember, in a polar solvent, the delta H was 0. So actually, in this case, the enthalpy is helping us. So let's see what happens to the delta S. Okay, so what we're going to do now is, again, we're going from something in the protein being like freely floating around to something that's more ordered. Because we're decreasing that freedom of motion for the protein, we're going to say that the delta S is also, for the protein itself, because it's increasing in order, or it's an unfavorable change in entropy, because it's now becoming more ordered, we're going to say that the entropy of the protein is going to be negative. Now, for the solvent, if you remember in a polar solvent, we said that the delta S greatly increased because of the hydrophobic effect, okay? However, in a non-polar solvent, there is no such thing as a hydrophobic effect. There is no water cages. There's no such thing as a hydrophilic effect either. The solvent is never held in place and restricted into cages, okay? And this applies in a non-polar solvent. So in a non-polar solvent, we say that the delta S is also going to be 0, okay? There's no water cages, so there's nothing about freedom of motion here. We're all good, okay? So overall, the delta S of the protein is, or the delta S of the system is going to be negative. Now, if we take tally of this, remember the delta H we want it to be negative to make delta G more negative. That's very good. And in reality, we want the delta S to be positive because that makes the delta G in turn more negative. However, in this case, if you look at the delta S, it's also negative. So together, if you take these two, this is a positive number. If you take this one, this is a negative number. So then what happens to your delta G? Well, if you were trying to figure out if your protein was going to fold in a non-polar solvent, what you would have to do is you would have to compare the magnitudes of delta H versus T delta S in order to determine if your protein folds, if protein folds. So, okay, you have to consider, and this is again has to do with the delta G. So you have to consider both the enthalpy and entropy, and whichever term is bigger, that'll determine protein folding. So if, for example, if the delta H is more negative, that means that this term is going to be bigger than the T delta S, so that we can say that the protein folds spontaneously. However, if instead the T delta S term, this was bigger, then we're gonna have this positive term outweigh the negative term of the enthalpy. So overall, we're going to make the delta G positive. So it depends. So the key takeaway here is that in a nonpolar solvent, the delta H is favorable because we are forming stronger bonds in the products with the H bonds. But the delta S is going to be unfavorable because our protein is gaining more order while we have no water cages to increase the entropy of the solvent. The entropy of the solvent is 0. Okay, so we have to consider both in order to determine if our protein is going to spontaneously fold in a nonpolar solution.